Welcome back, viewers. In this lecture, we shall be considering the following topics: law of gravitation, but this would be in terms of calculation; differences between acceleration due to gravity and universal gravitation; magnetic field. This would be in terms of question and answers. But before we continue, I want to remind you of our upcoming quiz competition that takes place every first Saturday of every new month. So our next quiz competition would be on the 7th of September 2024. The subscribers you are seeing on the screen, which I'm about to project, are our previous winners. And I want to say that you too can stand a chance to be celebrated. Okay, so let's move down to today's questions. This question says, calculate the force of attraction between a star of mass 2 times 10 to the power 30 kg and the Earth, assuming the star is located 1.50 times 10 to the power 8 kilometers from the Earth. Take the mass of the Earth to be 5.98 times 10 to the power 24 kg and the gravitational constant G to be 6.67 times 10 to the power minus 11 Newton meters square per kilogram square. Take G to be 10 meters per second square. Okay, so whenever a problem like this is given to you, you have to first list out the quantities. When you do that, you will have an idea of which expression you are to use. So we begin to list. Here we have G equals to 6.67 times 10 to the power minus 11 Newton meters square per kilogram square. Mass of the Earth 5.98 times 10 to the power 24 kilogram. Mass of the star 2 times 10 to the power 30 kilogram. G 10 meters per second, and the radius, the distance of separation between the Earth and the star, is 1.50 times 10 to the power 8 kilometers. Looking at the SI unit of other quantities, you see that they are being written in terms of the base unit and call it fundamental units. But that of the radius here is in kilometers, so we still need to convert these kilometers to meters, which we will do. And here we have 1.50 times 10 to the power 11 meters. I hope you know how we did the conversion. Kilo here represents 1000, so we multiplied 1000 with this value. When you do that, you will get the new value that comes with the index 11. So that's just what we did. Okay, so let me proceed. Now come up with the expression F equals to GMSME over R squared. The next thing is to substitute these values accordingly. And then the radius is squared. When you simplify it, you get the final answer 3.55 times 10 to the power 22 Newton. So that's the solution to that very problem. The next one says, state the differences between the acceleration of free fall g and the universal gravitational field. Okay, so solution. These are the differences. G and small g, capital G and small g. Unit of capital G is Newton meter square per kilogram square, while unit of acceleration due to gravity G is meters per second square or Newton per kilogram. Then we also have another point that gravitational constant is the same everywhere, but acceleration due to gravity G varies from place to place. Gravitational constant is a scalar quantity, while acceleration due to gravity is a vector quantity. So take note of that. Let's move down to the next question. This other one says a coil of an electric generator has 500 turns and 8 centimeters diameter, full stop. If it rotates in a magnetic field of density 0.25 Tesla, calculate the angular speed when its peak voltage is 480 volts. Take the constant pi to be 3.142. Okay, so let's list out what we have. Number of turns 500, and then the constant 3.142 is given. Diameter is given to us, and of course from this diameter we have to deduce the radius, area, and it's from the diameter we would get the area, which we are going to use in this problem. Okay, so diameter is equals to 2 radius. When you combine 2 radius, you get a diameter. So if we make the radius the subject, we have d over 2, and then we now substitute the value of diameter into d and divide by 2. I didn't do that, but I want you to do that yourself. Okay, so recall that area equals to pi r square, and pi is given in the problem, so we are going to substitute the value of pi, which is 3.142, and then the radius is 0.04. We are going to square it, and when we square it and simplify it, we will get 5.0272 times 10 to the power minus 3 meters square, which is the area. And then the magnetic field B is given to be 0.25 Tesla. After listing this, we are asked to find the angular speed, which is omega. So we are to pick a suitable expression that will suit this very problem. But recall that E equals to BAN omega. When we make omega the subject, because we are to solve for the omega angular speed, then we have E over BAN. Now all we need to do is to substitute the values that is given in the equation. When you substitute the given value, then you will get the final answer, 763.8 radians per second. I want you to do the substitution yourself so that you will understand it better. Let's consider this other example. This one would be like a classwork and you will solve it. This one says the coil of an electric generator has 500 turns and 8 centimeters diameter. If it rotates in a magnetic field of density 0.25 Tesla, assuming the angular speed is 700 radians per second, though I didn't write that, 700 radians per second, calculate its peak voltage. Take pi to be 3.142. So you are going to use the expression that we have given, or I have given above, E equals to BAN omega, and then solve for the peak voltage. When you do that, you will arrive at this answer. That one is for you. Okay, let's look at this other question. This one says, what are the poles of a magnet? What are the poles of a magnet? The poles of a magnet are points on the bar magnet where magnetic field are strongest. So you have the strongest magnetic field at the poles of a bar magnet. This one says, what happens when two magnets are brought close to each other? What happens when two magnets are brought close to each other? They exert a force on each other. When you bring a magnet close to another magnet, there is bound to be an interaction of force. So they exert a force on each other. This one says, what happens when two like poles of magnets are brought close to each other? When two like poles of magnets are brought close to each other, they repel each other. So if I bring the north pole of a magnet close to the north pole of another magnet, they are bound to repel. If I bring the south pole of a magnet close to the south pole of another magnet, they will also repel because they are like poles. What happens when two unlike poles of magnets are brought close to each other? They attract each other. They attract each other. Let's look at this figure here. So this is a bar magnet. I want you to look at this figure critically because you don't know where you would come across this. So this bar magnet has a north pole here and a south pole. You can see the direction of the field. It starts from the north pole and ends at the south pole. So the arrow is pointing outward from the north pole, but for the south pole, the arrow is inward. So please don't get confused about this. It's written here, this is a bar magnet. So here this one says, unlike poles of a magnet attract. So this figure here is figure for unlike poles, and the magnetic force starts from the north pole. So you see the arrow here coming out from the north pole and terminates at the south pole. So if you draw the arrow from the south pole, then it's not correct. Take note of that. Okay, so let's move to the next slide. Look at this other figure. You have two like poles and a point in between the two poles marked X. That point is referred to as the neutral point. The point labeled X in the figure is called the neutral point. This is a point on the magnetic field where the magnetic force is zero. It occurs when magnetic field produced by the magnet is exactly cancelled out by an external magnetic field. So that point you see on that figure is called a neutral point. If you are being asked a simple question, what is a neutral point, you should be able to attempt such question. Okay, so the next question that we have here is this. This one says, what type of force is magnetism an example of? What type of force is magnetism an example of? A non-contact force. Remember, we have contact force and non-contact force. Alright, this one says, what is an induced magnet? What is an induced magnet? The material that becomes a magnet when it is placed in a magnetic field. A material that becomes a magnet when it is placed in a magnetic field. Let's look at this one. This one says, what happens to an induced magnet when it is taken out of a magnetic field? What happens to an induced magnet when it is taken out of a magnetic field? It loses its magnetism quickly. It loses most or all of its magnetism quickly. The next question here, what is magnetic field? What is a magnetic field? It is a region around a magnet where the force acts on another magnet or on a magnetic material. Magnetic field is a region around a bar magnet where the influence of that magnetic field or that magnetic force is being experienced. What materials are magnetic? In other words, one can say, what are magnetic materials? We have up to 5 here, so you have to memorize them in case you see them another time. Most of the times they may put them in multiple questions and you are asked to find which of the following is not a magnetic material. So just memorize this in case you come across something like that. This question says, what materials are magnetic? We have iron. Iron is magnetic. Cobalt is magnetic. Nickel is magnetic. Steel is magnetic. And manganese. So we have iron, cobalt, nickel, steel, and manganese. I do use this short form to recall it most times. You can just say Ni MSC. Ni MSC. Okay, so N here represents nickel, I is for iron, M is for manganese, S is for steel, and C for cobalt. If you like it, you can as well use it too. Okay, so let's move on. Let me minimize this one. List applications of electromagnets in industries. List the applications of electromagnets in industries. We have electromagnets. Let me take this up. Electromagnets are used in producing magnetic fields required in generators and electric motors. They are used in producing magnetic field required in generators and electric motor. They are used for lifting and transporting heavy pieces of iron and steel in industries. They are used to separate iron from mixture, especially those that contain non-magnetic substances. They are used in construction of electromagnetic devices such as electric bell and telephone earpiece. The next question says, what happens when a current flows through a conducting wire? What happens when a current flows through a conducting wire? A magnetic field is produced around the wire. So whenever current is passed through a wire, that wire automatically behaves as a magnet. Magnetic field is generated. This one says description of magnetic field pattern for a bar magnet. Description of magnetic field pattern. Look at this figure. I think this one is clearer. This is a bar magnet. And look at the direction of the magnetic field. So you see where we have the North Pole, the direction. Okay. Alright. Let's read the next question. What does the strength of a magnetic field depend on when a current flows through a wire? What does the strength of a magnetic field depend on when a current flows through the wire? The strength of a magnetic field depends on the size of the current and the distance from the wire. The size of the current and the distance from the wire. Someone say, what is a solenoid? Solenoid. It's a coil of wire. What happens to a magnetic field when a wire is shaped into a solenoid? What happens to the magnetic field when wire is shaped into the solenoid? It becomes much stronger. So when you have the solenoid and then wire is put inside, the magnetic field becomes much stronger than what it was initially. Describe the magnetic field inside the solenoid. Describe the magnetic field inside the solenoid. The magnetic field is strong and uniform. It is strong and uniform. It has the same strength and direction at every point. How can the strength of the solenoid be increased? How can the strength of the solenoid be increased? The strength of the solenoid can be increased by adding an iron core. What is electromagnet? A solenoid with an iron core. Draw the magnetic field pattern for a solenoid. I think we can see one here. You see that it's a coil of wire and you see the magnetic field pattern around it. How can the magnetic field of a solenoid be stopped? How can a magnetic field of the solenoid be stopped? It could be stopped when it is turned off. When you turn off the current. Okay, so draw a magnetic field pattern for a straight wire carrying a current. Draw the magnetic field pattern for a straight wire carrying a current. So this is the pattern. The side where you have the thumb represents the direction of the current. I will still come back to this. Then where you have the finger of this human represents the direction of the field. List any two rules which can be used to visualize the relationship between current direction and magnetic field direction in a current carrying conductor or solenoid. Let me take it again. List any two rules which can be used to visualize the relationship between current direction and magnetic field direction in a current carrying conductor or solenoid. The solution here is the clenched first rule. If you don't call it clenched first rule, you call it the right hand grip rule. And the second one is the corkscrew rule. Okay, so state the right hand grip rule. The rule states that if a wire is grasped or is held with the right hand so that the thumb points in the direction of the current, then the direction in which the fingers are coiled indicates the direction of the magnetic field. As you can see the figure here, you see the hand of the human, and you see the direction of the thumb. That direction of the thumb represents the direction of the current, and other fingers indicates the direction. This is the direction of the current. It's going this way according to the rule, and other fingers represents the direction of the magnetic field. That's what that law is trying to state. So look at it very well and get that understanding. Okay, so let me proceed from here. State the Maxwell's corkscrew rule. The rule states that if the right-handed corkscrew is turned so that its tip travels along the direction of the current, the direction of rotation of the screw gives the direction of the magnetic field lines of force. You will have to imagine using a screwdriver to pierce into a cork. While you are rotating the screwdriver is moving in a straight line, moving forward. So the direction of the screwdriver represents the direction of the current, and the rotation of the screwdriver tells you the direction of flow of the field. That's just what the Maxwell corkscrew rule is trying to say, which is almost the same as the first one. So the two rules tells us about the direction of current and about the direction of the field in a wire. So look at these figures. The first one here in consideration tells you the direction of the current I, and then the direction of the field. Let me call this B. Now, if the I is facing this way, you now have the field moving the other way. Is that okay? Also study that rule and get that understanding. Okay, so this is our channel email. In case you want to contact us, you can use or you can meet us through this email. This is our home page, and I want to say thank you for watching. I want to say thank you to our subscribers, and I want to encourage them, always try and share our posts to your friends. I would really appreciate it. Also, try endeavor to be making comments. Click the like button. It shows that you appreciate the video you are watching. This is our home page. In case you are watching us for the first time and you are yet to subscribe, please, I want you to try and click on the subscribe button. When you do that, it will appear to be subscribed as you have seen here. The reason for subscribing is for regular notification. So anytime I upload a new post, you would be notified. Thank you for watching and have a wonderful day. I hope to see you in our next lecture.